Hello everyone, and I hope you are doing well everywhere you are. As you remember, in the previous video I created a hexagonal structured mesh for our geometry, actually a shell and tube heat exchanger. And now I'm gonna do its numerical simulation using Ansys Fluent. So at first I open its workbench file and I've just improved the quality of the mesh for our purpose. So I'm gonna open it. Okay, it's my final mesh and I open it. So let me have a short look at our mesh in different cut planes. This is the shell mesh, and now I'm gonna show 3 cut planes. For example, cut plane normal to the x-axis. Okay, 1 0 0, and now I enable the volume elements, disable blocking. As you can see here, we have internal and external grids around and inside inlet outlets and also the tubes, and its quality seems to be good. Okay, or in the y direction, actually normal to the y-axis. Okay, it's okay. And now normal to the z-axis. We can improve the quality of this region, for example, or this region, but for doing a numerical simulation, this quality is acceptable. There is no problem. And now I'm gonna check the mesh. Okay, cut plane. apply. I'm gonna check the mesh to make sure that there's no problem in our mesh. Multiple edge is not an error, it's just a warning, okay? And in our geometry, it's normal, okay, because of baffles. And it's not a problem, so I ignore it. And now I'm gonna check the quality of the mesh in quality criterion and apply. Okay, the worst elements have quality of 0.24. It's gonna be great for starting our numerical simulation. There will be no problem with convergence. And as you can see here, the majority of the elements have the best quality, around 1. Okay, so it seems to be a good mesh. And now I'm gonna open Ansys Fluent to do our work. So I use Ansys Fluent element and link them. Okay. I'm gonna use double precision, and I'm gonna select 6 processors for our numerical simulation. I've prepared a file for our work in Mind Manager, and now I'm gonna proceed according to this file. It'll help me to have a better view of my problem, and it'll help me to avoid making any mistake. So at first I should scale the mesh if it's necessary. Actually, I'm gonna check its dimension. So I'm gonna use centimeter for length unit, and now its dimensions are good and there is no need to scale my mesh. Okay, its dimensions are correct. So I close it, and after I should check the mesh to make sure that there's no problem. Okay, what is important? It's the value is the value of minimum volume. Okay, it must be a positive number. Okay, and now it's positive, so there's no problem with the mesh. After that, I set these options. For example, for solver, I use pressure based because our fluid flow is incompressible, and I'm gonna solve my problem in a steady state. And for gravity, it's in the minus y direction. It's in the opposite of y-axis, minus 9.81. And so in the model module, I should enable the energy equation, and for viscous model, I should select a turbulent model. Note that my problem is turbulent based on the Reynolds number for flowing over the tubes. Okay, for the external flow passing over the tubes. So I'm gonna choose a turbulent model. Actually, its Reynolds number is 2000 based on what I've calculated. So I'm gonna use K epsilon model for my simulation. And now in the model module, I use K epsilon. Actually, I enable the energy equation, and for viscous model, I choose K epsilon model. Okay. And now in the material module, for fluid, I should choose water, and for solid, aluminium. Note that in my numerical simulation, I'm not gonna solve the conduction equation. So my solid parts such as shell, baffles, and so on doesn't have any thickness. Okay, so it doesn't really matter what kind of material I'm gonna choose for the solid part. Okay, it has no effect on my simulation because I'm not gonna solve the conduction equation. So I add water to my setup Fluent database, and I'm gonna choose, water liquid. So I copy it, and for solid, there is no problem with aluminum. After this step, in the cell zone conditions, I'm gonna choose water. So in fluid, this is the volume part of our mesh. Okay, actually it's interior regions in our simulation. So I'm gonna choose water because both fluids are water. Okay, passing through shell and passing through tubes. And I'm gonna set the boundary conditions starting with baffle. Okay, it's a wall. For momentum, I'm gonna choose a stationary wall with no slip condition. And for thermal, I'm gonna choose heat flux with coupled option because the baffles are between the cold and hot fluids. So I'm gonna choose coupled boundary condition with 0 wall thickness because I don't want to consider conduction through this boundary, as I stated before in this part. So for baffle, a stationary wall, no slip, and for thermal, it's coupled. Okay. And now for shell as well, it's a stationary wall, and for thermal I set heat flux boundary condition with 0 value, because I assume that it's insulated. Okay, it's assumed that the heat exchanger is insulated perfectly, so no heat will be transferred during this wall. So for shell part, I'm gonna use heat flux with 0 value. Okay. And now for shell inlet, it's an inlet, so I'm gonna choose mass flow inlet for this boundary with mass flow rate of 0.003 kilogram per second. And for thermal, its temperature is 290.15. So mass flow inlet, I'm gonna use normal to boundary option with 0.03 and 290.15. Okay, and now for shell outlet, I should set pressure outlet for it with 0 gauge pressure and thermal. Okay, the temperature of backflow is not important because we must not have any reverse flow in our outlet boundary. Okay, because it will be affect your post-processing. For example, you're gonna calculate the performance of the heat exchanger, and you need the average temperature on the outlet boundary. So we must not have any reverse flow in this boundary, and it doesn't really matter what value we are gonna set for this boundary. Okay, because we have no reverse flow in this region. So for shell outlet, I choose pressure outlet with 0 gauge pressure, and for thermal it's not important. For tube, it's a wall with coupled and 0 wall thickness, because I don't want to consider conduction through this boundary. Okay, it's an approximation. So I'll check it, coupled, and okay. For tube inlet, again mass flow inlet with 0.1 value and 325.15 Kelvin. So mass flow inlet, normal to boundary, and 0.1, and for thermal 325.15. And now this is the last boundary, pressure outlet 0, and again we must not have reverse flow in this boundary. So tube outlet, pressure outlet, with 0 value, and it doesn't really matter. Okay, and now I'm gonna solve my problem. So I'm gonna solve my simulation. We can monitor residuals as well as surface monitors in order to find out when our convergency is obtained. But now I'm gonna just solve the equations of motion as well as energy equation. So I initialize the problem. It's good. Actually, I'm gonna run the simulation with 1000 iterations. So its convergence trend is acceptable, and as it'll take a few hours to complete this solution, I'm gonna stop this simulation because I have a completed solution, okay? And I'm gonna open it. So I stop it at this stage, and now I close it. So I delete this element in order to set it again. I use CFD-Post in order to do post-processing, okay, such as plotting contours, the streamlines, and so on. So I'm gonna change the background to white. Actually, I use option and viewer, solid mode, and white color. It's better. And now, for example, I'm gonna plot the contour across this heat exchanger on a plane normal to the x-axis. So at first I create such a plane in y z plane 0, and okay, it's our plane, and I'm gonna plot the contour, actually the contour of temperature on this plane. So contour, and now for plane 1, temperature and local. For example, 100 is sufficient. Okay, this is the contour of our numerical simulation. This is the hot fluid flow, and this is the cold one. And you can change the appearance of the legend. using this option. For example, I'm gonna change to fix, or I'm gonna change its font. It's just a little better. And now I'm gonna plot the streamlines. So I disable the contour and use the streamline option. For example, streamlines that start from tube inlet forward. Okay, I can change the number of streamline, for example, to 50, and you can do whatever you want in this precious software. Okay, it'll enable you to do whatever you want, and it's so amazing. Okay, thank you so much for your watching, and have a nice time.